in charge of Gonzalo Tampier from the Universidad de Valdivia. He will present us experimental assessment of a floating wind platform.
Okay, so here we go. So I will present some of our research related to floating wind turbines, and I will apologize for some parts are related to control, and I am functional control and alphabet, so my field is hydrodynamics, so I'm sorry for that. So who are we? We are a group related to the wave and towing tank of Universidad Austral de Chile, and also we are part of the Marine Energy Research and Innovation Center, the Chilean Center of Marine Energy. And this project itself was part of a project with a startup, which is Okeanos, from a former student who's working now in France. So this is part of our team. Some of them are here today, and we work in Valdivia, in the south of Chile, in the wave tank. So about this project, very briefly about offshore wind. Of course, we're very interested in wave energy. We keep on working on that, but the installed capacity in the world is still quite small, and we have no reliable growth estimates of this sector in the coming years. So we don't want to put all eggs in the same bag, so we want to divert and diversify. So floating wind is, of course, a very interesting opportunity for us in terms of potential growth, and of course also in terms of the available technology from fixed bottom offshore wind, which is already an industry. And if you look at the map and see the development in Europe and the recent development in Asia and now in the North America, of course the question arises, are we the next region? And I think, of course, yes. And especially in countries such as Brazil and Colombia, which already have a strategy and are already on tenders for locations for offshore wind, and in the future probably for floating offshore wind. Of course, we see the resources abundant, especially in Argentina and Chile, but also in other spots in Brazil and Uruguay, in Colombia, La Guajira, in some spots in Peru. And we also see that our bathymetry is very diverse. So you have a big continental shelf in the south of Argentina, but we almost have no continental shelf, and there, of course, is the opportunity or the need for floating wind. This is not really important, but it's just a chart of the total technical potential of offshore wind in Latin America. And you see first place Argentina, then Brazil and Chile, and most of this potential is in the floating sector. So, but that's not all. We are not necessarily going to this big market from the very beginning. We think that niche applications are very interesting, especially in our countries. There are some isolated areas, there are some industrial needs, and we have identified some needs for aquaculture, isolated communities, environmental monitoring, coastal infrastructure, and of course the integration with other renewable sources, which have been spoken of here today. One of these applications, aquaculture, is especially interesting or important for us. We have a very large aquaculture industry in the south of Chile, and this is how a typical fish farm looks like with generators. They need some energy, not very much, but about 300 kilowatts of installed power for feeding the fish, and we have about 300 of those, so they're using today, everyday diesel. So that's our an interesting point to start with. We have experienced some projects with tidal, with wave energy, but there's not so much locations which are able for that, because these are sheltered areas with almost no waves, and the tidal streams, you cannot put one of these centers in places with, I don't know, interesting numbers for tidal energy, like 3-4 meters per second. You need a certain current speed, which is good for the fish. That's your priority. So The project I'm going to talk about is the development of a small-scale floating wind turbine for aquaculture and isolated communities. It's a project which was started as a startup. It's a startup Ciencia project with this company which was funded within the researchers from the university a few years back. And the idea is to develop a very simple modular floating wind platform with a power of about 50 to 150 kilowatts to be a competitive alternative to diesel. And our job was around all these design aspects, including hydrodynamic design, structural arrangement, mooring systems, and try to minimize motions in waves, wind, and currents. And we also had a very strong interest in logistics and manufacture, so that we are able to build and manufacture and do the maintenance with the capabilities we already have, with the ships we have, and not building something that we cannot deploy or fabricate later. So for this, we made a design exploration with different, a parametric design with different semi-submersible platforms, most of them in 3 columns, others as a pontoon. And here you see what we try to minimize: accelerations on the nacelle, and the cost. The cost, of course, is a very broad estimate, considering the amount, the mass of steel, with some very basic stiffness calculations, and of course also the materials, the different materials. In general, most of these solutions were around 10 to 15 meters long, 5 to 20 meters depth, and a displacement around 50 tons, so quite small. The hydrodynamic response was modeled with NEMO. As I mentioned, we made some basic beam calculations for the structural elements, and we made with that some cost estimates, and the idea was to minimize cost and nacelle accelerations. And finally, we came to 2 designs which were a little different, but both very interesting. One of them was a typical 3-cylinder design, semi-submersible, which could be built out of steel or a hybrid steel and concrete. And the second design was a pontoon with a moon pool, which was out of concrete. For these 2 models, time domain simulations were made, some mooring options were evaluated, and a more detailed structural design and more detailed economic evaluation was made. That was not part of our team in Valdivia, but from the startup. With this evaluation in hand, the final selected design was the pontoon design, mainly because of cost reasons and also for practical reasons. This pontoon had some volume that can be used also for other uses in the salmon farm, and also the concrete building, but the material is far cheaper, and that made it very interesting. And also from the maintenance point of view, you don't have to put it out of the water to paint it every 5 years. You get practically a lifetime device for many years to come if you build it right. So our experimental campaign of a model was, we used a 1:25 scale model, and well, Jose Miguel already showed some pictures of our tank. We developed with one of the participating companies a very basic system to simulate the rotor thrust with some drone motors. And we made experiments in regular waves to validate our numerical models, and some experiment in irregular waves under operational and also under extreme wave conditions. So this is our model, and this is the way I present my excuses, because this is basically a closed loop system where you have a load cell where you measure the actual thrust, and you compare it with the thrust force you have programmed. And with this difference, the system will change the velocity of the motors or the voltage of the motors accordingly, so that to match this desired force. So we have a nearly constant force on the system, on the mast, which is equivalent to the thrust you want to achieve. Of course, it's not fully realistic. There are many differences with the real aerodynamic thrust on a turbine, and we are currently in a second project where we are working on an upgrade, including a new LabVIEW interface, and allowing to have a time series input, and also hopefully, we still don't know if this is going to work out, a real-time variable for a software in the loop, such as MERIC or other codes where we can calculate the aerodynamics of the turbine in real time. One of the changes also we recently made is that we are able to make forward and backward thrust, which is useful for some of the experiments. So this is the experimental arrangement. This is the middle of the tank. We have some mooring lines. These are the rather long regular waves, as you see. We have some wave gauges around that cannot be seen in the video. We have in the back 4 motion capturing cameras and our irregular wave generator with absorption, which is working here in flap mode. It can work in flap and in piston mode. So the experimental campaign included 25 regular wave frequencies without thrust, some regular frequencies with thrust, with the thrust system activated, and also 7 operational sea states with and without thrust, and 2 extreme sea states without thrust, of course, because on that conditions the thrust is not important. The turbine should be shut off out of like in survival mode. So some of the results in regular wave, here you see the heave response amplitude operator, and the curve is the results from NEMO, which are quite satisfactory, besides, of course, the resonance peak. Here we have the pitch response amplitude operator, and we were satisfied with the performance of the code for further improvement of the numerics, and also seeing that our experiments went okay. On the irregular waves, here are some time series of the operationals for one of the operational sea states. It's important to mention that these sea states are in sheltered areas within the channels where these centers are. It's not the open ocean, so there are some spectra here of the response spectra of heave and pitch, and similarly also the same operational sea state with the thrust system activated. So here's a comparison of this system, the significant heave and pitch amplitude, and you see that there is a certain impact of the thrust mechanism. It changes the response of the system, which is something that can be, of course, expected. And you see here 4 operational sea states of 0.62, 1.1, 2, 0.19, and a final sea state which is a little smaller but with longer waves, which could be a location with a little more swell, a little more exposed in operational conditions. And also our extreme sea states, the most extreme sea state we tested, as I mentioned, is a shelter place, has a significant wave height of 3.75 meters, so roughly the maximum wave height of 5-point-something meters, in a peak period of 9.2. And you see that, yeah, it's not optimal, definitely not. We have some input here for the mooring design, but we had also large concern about green water on deck, and this is something we're working in the next iteration of the design, which will be subject to several changes to avoid these conditions. But in general, it was a very positive experience, and now we are on our next in a second project with the same partners and also with some new ones, where we are developing a larger prototype. It's a 1:2 scale prototype with a 15 kilowatt turbine, and hopefully next year, by the end of the next year, we should be installing the prototype in a shelter place close to a salmon farm in the south of Chile, close to Chiloé. And the idea still is around building a concrete design, probably because of cost, and keeping these additional design considerations for installation and maintenance using the local ships and the local capabilities of the small shipyards, which provide lots of structures, ships, and naval artifacts to the salmon industry. And of course, this prototype will be sensorized, and we hope to make some real environment tests and contribute to the final design of the 1:1 scale prototype. But this is still work ongoing and at the very, very beginnings. So as conclusion, the results we obtained were satisfactory for the validation of our numerical tools. design of the floater is satisfactory under operational conditions. It was below the accelerations we set as limiting, but it could be potentially problematic under extreme conditions, and this is why we are in the process of a redesign, taking other new considerations on the practical aspects, and of course always economic considerations. This is a startup that is working with us on this, and they're really confident that this will be an interesting business for them. And yeah, we are of course very interested in keep on developing our thrust system and making some new friends or people that can help us on that. We're grateful, and also seeking for collaboration locally with other specialists. So that was what I wanted to tell you. Thank you very much.
Thank you. We have time for questions.
I always have a question, sorry. So it's interesting that you're using 4 small turbines to simulate the wind effect on the platform. And it's interesting that if you have one of these deployed at sea, the pitching effect of the platform has got a negative effect on the turbine itself, because you get cycling of the pitch controller, which will eventually wear out the pitch controllers. So one of the projects that we have that I'll maybe mention a little bit about tomorrow is a combined wind wave system, where part of the objective is to stabilize the platform to take some of the axial load off the turbine. But the system that you have actually would be a very good test bed, because on the one hand we're trying to stabilize the platform, but you can actually do that using the pitch controllers as well, so you actually have an experimental system that could work well, minus the wave actuators. But I think that's one of those areas where a combination of technologies can work in harmony, and there are some studies that you can show where you get both benefits from wave actuators, that you actually manage to harvest some energy, but you also manage to help to stabilize the platform. And it was interesting in your video there, you can see quite a lot of pitch motion, and that's not unusual, I think, with most floating offshore wind platforms.
Yeah, it's important to consider that since these are very small turbines, they normally don't have pitch control. So the one we are building now with 15-20 kilowatt will by no means have pitch control, but the larger one with 100 kilowatt probably will. So that there's lots of questions, and small turbine manufacturers also are not really very open to provide much information. And there's also no benchmark turbine in this size, which is not the case with bigger turbines, where we do have a little more information, or these NREL turbines or validation turbines. So yeah, it's a bit challenging, and definitely the combination with wave energy could be very useful in this case. Of course, the problem there is adding complexity is also a problem. Some people say, oh, let's forget about wave combination, because we could add 1 meter in the rotor and get the same energy. But of course, there is also a bidirectional benefit in this by minimizing pitch. There's also other technologies. For example, one of them is being developed in Australia, Moor Power, which is harnessing the energy of such floating pontoons using the mooring system with winches. So that could be also an interesting combination. We're doing some contacting there to see if this is an interesting possibility as well.
Okay, we have time for another question.
Yes, just a small one, short one. Maybe I miss it, but how is the working the orientation of the turbine?
The orientation?
Yes.
The platform remains fixed, and it will use the yawing system of the turbine, just as in the same way as it would be on land.
Mm.
Yeah.
So it is active.
Sorry?
It is an active orientation.
Yeah, it's an active orientation.
Thank you.
Yeah. In the salmon farms, normally you don't have so much space. We thought about the idea of being passive with a full platform, But these maritime concessions are not really so big, and we have to avoid using much space as needed because there is not much more space. So you have an area where most of the area is already used by the farm. Then there's some clearance to the floating pontoon, and somewhere in between you have to locate the turbine, but you cannot have a long fairlead to rotate as it would be ideal, I think.
And you have independent control of the wind velocity, of the turbine velocity, each turbine velocity?
Yes, in this basic version, the results I showed, no, we didn't. But now in the second stage, we will have at least for 2 and 2 separated.
2 and 2 or 2 and 2?
2 and 2. Especially because in some motions, in large amplitudes of motion, actually to maintain the thrust, because of the mass you have on there, you may want to reverse the thrust. The turbine, the real turbine, will have some damping in the motion, and to accommodate to this force, you may need to have some reverse thrust in some circumstances.
Thank you very much.
Okay, any more question about this? Yes.
Hi, well, thank you very much for the presentation. Really interesting presentation. I was wondering if you could dig something about for the size of the turbine that you are trying to build in the future, the 1-on-1 scale. Which would be the conditions that you mentioned, survival conditions, the conditions by which the turbine should be shut off? I mean, I don't know if it's wavelength or something in the water. I mean, what would be the measurement by which the turbine should be shut off because it would be dangerous for a turbine? I was wondering if you could dig that anywhere.
Yeah, good question. It will depend on the turbine manufacturer. Normally, depending on the class of turbine you select, you will have something 20-something to 30 meters per second. And normally this shut-off condition is only related to the wind speed because they are designed for that. So... yeah, you were one. Yeah,
I was
right.
wondering more about the sea conditions. I know that the wind is more or less 25 meters per second. It's the typical cut-off wind speed. I was wondering in the sea conditions if something about the waves, it was a parameter to take into account.
It's a very good question because we should address that in the prototype, and also from it will depend on the wind turbine manufacturer. There is some information on thresholds for maximum accelerations on the nacelle, for example, and also maximum angles. These are the two aspects, and there's no really a consent in the literature about that. Some say, I don't remember, I'm bad at remembering numbers, but the angles should be no bigger than 3 degrees or 5, and others say about the acceleration. So we made a table of all of these declarations in literature, in papers, and there's not a really agreement about that. And of course, it will depend on each manufacturer. The manufacturers of small turbines are less concerned about that. That's very interesting also. The smallest ones, for example, you can put them on boats and they work without any problem. And the bigger you get, of course, the accelerations are more problematic and you are more on the limit with the structures. So I think for the smaller turbines, we shouldn't have any concerns about having limiting accelerations or limiting angles for these very small turbines, but that will change once we go for the 100 or 150 kilowatt turbine. But we still don't know because the manufacturers of the turbines will not give out that information before we buy it, sadly.
Thank you very much.
Thank you.
Okay, thank you very much, Gonzalo. Presentation.